Okay, so we have with us an alumni of Ohio State University as well as alumni of this class. So Jianzong was my student a few years back. He's here today to relive his old memories of ECE 57, 59 in his time and now 5500. Okay. So we'll talk about approximate dynamic programming today. We have been talking about dynamic programming. So we talked about Pontryagin minimum principle, which is a necessary conditions for optimality. Then we talked about dynamic programming, which is sufficient condition for optimality of closed loop policies. Then we talked about how to apply dynamic programming algorithm to derive optimal control policies. So that part is done. Now the problem is in most of the real world problems that you might encounter in your day-to-day life, you wouldn't be able to actually solve the problem. So solve the problem using dynamic programming. So there are multiple ways that people have come up over the past few decades since 1950s, which allows us to, so we have this original dynamic programming problem, which may be very complicated, very high dimensional, very large number of time steps, and so we cannot really solve it. So what we need to do is come up with a simpler problem that we can solve within the time limitations that are given to us. So if you are running the optimization algorithm on an ECU or on a microcontroller in a vehicle and it needs to finish within 100 milliseconds, then you need to come up with a specific approximate dynamic programming algorithm. If you are going to control a satellite on Mars, or somewhere in the outer space, then you need to come up with a different approximate dynamic programming algorithm. And if you are controlling something using a data center, so for instance, Google controls their air conditioning load on the data centers using the compute that is available within the data center. So in that case, you have a lot more computational power, so you can do a lot more sophisticated dynamic programming in that situation. So depending on the computational limitations, depending on the memory limitations, you will have to come up with some sort of approximate dynamic programming algorithm for solving that problem. So what are the general tools and techniques? So those are the things that we'll be talking about. Broadly speaking, when you think about approximate dynamic programming, these are the things that we need to worry about. So let me write down what the original problem is. And I want to minimize over all policies pi t that maps xt to ut of ct plus 1 xt plus 1 plus summation t equals 0 to capital T. So this is the problem statement that we have. This is what we want to solve. We may have a bunch of constraints. Let me write it as gt xt ut less than equal to 0 for all t. That gives us a constrained dynamic program. And now we need to come up with a way to solve it. So here are like 5 very broad techniques that people have come up with over the past few years. So there is a cost value function approximation. Second one is model / policy approximation. Third is look ahead approximation. Fourth is optimization. Approximation. and then there are hybrid methods. So hybrid methods means you use a combination of these techniques in order to solve the problem. Okay. Let's go into it. So what is cost and value function approximation? So we have some complicated nonlinear cost. We will replace it with a linear function, or we'll replace it with some combination of basis function. Same thing happens for the value function as well. Large part of reinforcement learning actually does value function approximation. I know some of you are studying reinforcement learning or will be studying reinforcement learning into the future. So reinforcement learning kind of does all of these things, but one of the more pronounced usage of reinforcement learning is in value function approximation. So we do that. In the model and policy approximation, we have a nonlinear system. We will replace it with a linear system around the equilibrium point. This is how airplanes, for instance, are optimized, because you know that the passenger airplane is mostly going to be cruising for most of the time, except for the ascent and the descent phase. So those are the two phases where things change quite significantly. But when you are at cruising altitude, you can kind of assume that there is an equilibrium trajectory, and you are only going to do a linear variation around that equilibrium trajectory. So that's the same as doing a model approximation. So you have a nonlinear model, but you replace it with a linear model around the equilibrium trajectory. In the look ahead approximation, remember, if we recall from that class on rocket, when we were talking about this this rocket optimization problem, this capital T was 1.8 million. We didn't want to solve a dynamic programming problem with 1.8 million time steps. So then we'll do the look ahead approximation, where we'll only do optimization for 10, 15 or 20 or 100 time steps. So that's look ahead optimization, look ahead approximation. And the fourth one is optimization approximation, which is somewhat less understood, but something that my research group has done a lot of work in optimization approximation in the past 4 or 5 years, which is something we'll be talking about today. Where what we do is, okay, we have this sophisticated problem, we have a solution to this problem already, but now some things have changed. GT has changed slightly, CT might have changed slightly, or this FT might have changed slightly. So as an example, you know, you are going in a flight, and because of the fuel burn, the mass of the flight changes during the entire duration of the flight. Same thing happens with the rocket. So you have the optimal trajectory for the flight and how you want to control it. So you have all that information, but because the mass has changed, the FT has changed itself. And so then the question is, your model has changed slightly, because it's not like the mass is changing significantly. The mass is only changing slightly. So your model has changed slightly. How do you do the optimization approximation and solve this whole optimal control problem somewhat easily? You could have changes in the cost function. This typically happens, for instance, you are running an air conditioning system in your vehicle, and then you feel a little bit hot or you feel a little bit cold. You turn on the temperature, you move the temperature a little bit up or down. So that's changing the cost function for that particular optimization. And but only slightly. You're not changing the cost function significantly, you're only perturbing it slightly. Or alternatively, you have a car, you're driving a car and a vehicle comes in front of you on the highway. So then your constraints change slightly, because now you have to make sure that you are maintaining the distance with respect to the vehicle in front. So that's changing the constraint slightly. And so again, the goal is to be able to approximate the optimization algorithm itself and be able to find out what the new solution is going to look like under the new conditions, under the new state dynamics, and under the new constraints. So that's optimization approximation. Any questions so far? Yes? Yeah, so policy and model approximation. So you have this function f of t. This is the model. This is the dynamical model of the system. and then policy is pi of t. And what you do is you have a nonlinear system, but then you linearize it around the equilibrium trajectory. Okay, so that's a model approximation. Policy approximation would be you can pick any control policy here, but then you restrict yourself to PID controller or a lead lag controller or a linear controller. So that's policy approximation. You could pick any nonlinear function as policy, but then optimizing it becomes difficult. So you just simplify the policy space itself, and then you optimize within that simplified space. Okay, so that's policy approximation. So when you see, like, if you look at your dishwasher and your I don't know what is that called, washing machine, all of them are using PID controllers. Okay, a lot of vehicles, a lot of things that are happening in the vehicle, they are all using PID controllers, and they tune the gains of the PID controller in order to optimize the performance of the system, right? But what exactly are they doing? They are restricting their policy space to be just PID controllers. They're not doing some complicated, heavy computation just to optimize the performance, right? They're just making sure that the policy space is simple, tune a bunch of knobs, and then you are done. That's your optimal policy.
Optimizing over, like, they're restricting the base in which the dishwasher can move.
That's right, exactly. So that's the policy approximation part. Okay. Any other question? Okay. So today I want to start with optimization approximation today, and then we'll talk about look-ahead approximation in the next class. And then we'll talk about these 4 approximation stuff in the subsequent classes. So optimization approximation. So we have a bunch of papers on this, but today because the alumni is here, so I'll just talk about his paper. So this is optimization. This is a 2023 paper that we have written. This is singular perturbed system. So what happens in a singularly perturbed system? I have 2 states, xt plus 1 equals to xt plus epsilon. And I have the same optimization problem. I want to minimize over all policy pi t maps x cross y to u. And I have a constraint gt xt yt ut less than equal to 0. This epsilon is a small number.
Is that x cross y? What is it?
Yeah, x cross y. Because I have my state space is basically comprising of xt and yt. I have 2 states, 2 vectors. This constraint is for all t. How would you solve this problem? So let me tell you what is happening here. So I have 2 states, xt and yt. So this could be a, let's say, 5-dimensional space. This could be a 10-dimensional space. Okay, so these 2 can be vectors. I have a single action u of t. Now u of t could be, of course, 5 dimension, 6 dimension, 10 dimension. Okay, the only difference is this state is actually changing very slowly because there is this epsilon parameter which is very small. So this is a slow dynamics. And then I have a fast dynamics. Okay, so this yt plus 1 changes at every point of time, but xt changes very slowly. So I have slow dynamics and fast dynamics. Let me give you an example. So when I'm driving the car, I'm driving the vehicle, let's say one time step t to t plus 1 is maybe 1 millisecond. Okay? How much do I move in 1 millisecond? How much does my velocity change within 1 millisecond? Hardly anything, right? It's very small change. But when I'm pressing the accelerator, what do you think is the RPM of the engine, the rotation per minute of the engine? It's of the order of 1000. So the engine is actually reacting every millisecond. So I press the acceleration, the engine speeds up the rotation very quickly. And that's the engine rotation is actually happening at the fast dynamic scale. It's happening at the millisecond scale, but the position and velocity is actually changing at a second scale. Okay, and there is a difference of the order of 1000 in this particular case. So you can have a difference in time scale of the order of 10, 100 or 1000, and that becomes a singularly perturbed system. That's studied under this umbrella, singularly perturbed system.
So that means only single state space is changing fast.
Right. So there is, you basically differentiate the state space into two different state spaces, one that changes fast, one that changes slow. And this is, of course, there are only two set of dynamics. Generally, systems will have multiple time scales. So if you are looking at a chemical plant, if you're looking at a very large scale system like an aircraft or something, you will have things happening at multiple time scales. So we are just talking about 2 time scales here, but you could have like 5 or 10 different time scales within your system. Any other question? Yeah.
But like here, we are optimizing over a single state space. Here we are optimizing over 2 state spaces.
We are not optimizing, our state space is bigger. So here my xt, this xt is actually xt and yt from there. Okay, so you just have a bigger state space. Any other question? This same thing happens in the air conditioning system. So you are sitting in your vehicle, or you're sitting in your house, or we are sitting in this room. The air handling unit, which is somewhere, yeah, you see the vents here. So the vents are actually connected to the air handling unit somewhere above the vent, and so that is changing every 10 milliseconds or so, or 100 milliseconds or so. Do you think that the temperature of the room is changing in milliseconds? Not really, right? So the temperature of the room might be changing in 10 minutes, 15 minutes, and so on. So again, we see a situation where there are 2 different time scales of the system. So one system that works in millisecond scale, another system that works in seconds or minute scale. So now the question is, we have this very high dimensional system where the state space is very high dimensional, and we want to solve this optimization problem with constraint. So how do we go about solving this problem? So the first thing that we need to recognize is when I press the accelerator, there is an equilibrium RPM that we reach very quickly. So within a matter of 10 or 15 milliseconds, I reach an equilibrium RPM. When I'm changing this thermostat setting, which is right behind the room, I'm going to change the thermostat setting. I want to heat it up. Actually, I am cold right now. I really want to heat up the room. So if I want to heat up the room and I change the thermostat setting, the air handling unit is going to respond quickly. Within a matter of a few milliseconds, the air handling unit will change the position and will start pumping more air into the room, more hot air into the room. So there is an equilibrium in the fast dynamics that gets reached very quickly. Okay, whenever we make any changes, whenever we take an action, and we are at a specific point in the slow dynamics. So what I'm going to assume is there exists a function eta from x cross u to y such that f2 of x eta x u equals to eta x u. This is the equilibrium fast state. The second assumption that I'm going to make, I should probably write it here. If I look at yt plus 1 equals to f2 x yt u, so I'm fixing x and u at a specific point and I'm looking at the dynamics of y, then I have this condition I think we can use alpha here. So basically yt reaches equilibrium quickly.
Is this some kind of contraction mapping?
Kind of. Around the equilibrium there is a contraction. That's what this is saying. But it's actually a parameterized contraction because x and u are serving as a parameter, and then f2 is basically your contraction map. But only if you're looking at for every x and u, you're looking at the map f2, and that's a contraction map. And this is the fixed point of that particular contraction map. That's kind of what is happening here. Alpha is less than 1. So the third thing is that if you look at this GT, which is the constraint here, so this constraint has to be non-empty. It cannot be like if you are at an equilibrium at a specific x and u, then it's basically an empty set. We don't want that GT to become an empty set. It's just to make sure that the optimization is always well defined. The second constraint is that yt should reach the equilibrium very quickly. So this is the equilibrium point. This is the equilibrium fast state. So I change the thermostat setting, and the amount of airflow that is flowing inside this particular room, it reaches a steady state airflow very quickly. Okay, that's the yt, right? That's the yt here, which is how much air is flowing into the room per second. And it should reach the steady state as soon as possible.
So then why aren't we changing x and u?
So this is for every x and u. So no matter what value of x, so no matter what the temperature of the room is, no matter how much air handling unit I have turned on and off, the airflow to the room should reach the steady state as soon as possible. And it will actually reach the equilibrium exponentially fast. That's what this assumption is saying. Any other question? Yes. Interior is, so you know, like this is a set, this is a closed set, and so the interior is everything inside without the boundary. Okay, so like 1 less than x minus 1 less than 1, so that's the interior, and then the closed set will be minus 1 less than equal to x less than equal to 1. So it includes the boundary.
Where did you get the exponential notion?
This one?
Yeah.
So because alpha is less than 1, this convergence is going to be exponential. Exponential means that, let me write it here. So yt minus eta xu is less than equal to alpha raised to t y0 minus eta xu. This exponentially decaying term is there. That's what it means for exponential convergence. I mean, the reason why we call it exponential is this is e raised to t log of alpha, and this log of alpha is less than 0 because alpha is less than 1, so log of alpha is less than 0, so it's exponentially decaying. This is like e raised to minus constant times t, so that's exponential decay. That's right, towards the equilibrium value of the fast state.
So suppose if we consider now as 0,
Yeah.
we have changed it, we want to change the temperature, we want to increase the temperature, then in this meantime, the rate at which we should reach equilibrium should be
Very fast.
Exponentially.
Exponentially, yeah. You should exponentially reach the equilibrium. So do you drive a vehicle? No? Okay. So those of you who drive the vehicle, do this experiment. Get inside the vehicle, press your accelerator, and look at the engine RPM, and you will see that within a matter of a few milliseconds, the engine RPM would reach the steady state RPM. Okay, and as your velocity picks up, that equilibrium RPM will be changing. You will see it on your dashboard. So do this experiment, and hopefully drive safely. Don't crash while you are doing the experiment. Okay. Any other question?
So is there any equilibrium for the slow dynamics?
No, for slow dynamics there is no equilibrium. Generally for slow dynamics there is no equilibrium. I can change the temperature to whatever number I want to. Right? If you go to biology labs, some of the labs are at 50 degrees Fahrenheit. And if you come to my house, it's at 80 degrees Fahrenheit. So it's all over the place. XT is based on what the humans want. YT is something that's happening inside, which you don't see and feel, but it's actually is what driving the value of xt to the desired value. Yes, please. Right, so the speed, so if you think of xt as the speed there, you are right that the speed doesn't change significantly, but it still changes slightly because of the crosswind and a lot of things that might be happening in the environment. So because of that, the speed might change slightly. Yeah, that happens in the upper atmosphere. It's not like the air is completely still. There is still like things happening in the upper atmosphere. So that speed still changes. Aircraft is a somewhat complicated example. It's not as simple as a vehicle, because we are not pilots, so we don't understand a lot of those things very well.
I'm still not sure what you mean by it's the slow dynamics doesn't reach a steady state.
See, the slow dynamics is what people generally want. It does reach a steady state, but we don't care about how quickly it reaches the steady state. We care about only how YT reaches the steady state. So if I set my home temperature to be 80 degrees Fahrenheit, then XT has to reach 80. But how the air conditioning system, how much air it is pumping and not pumping, it's kind of invisible to me. I don't care about it. That's YT.
We're just not about the slow dynamic steady state.
We don't care about the slow dynamic steady state. And the reason is you care about the steady state when this t is infinity, close to infinity, that's when you start caring about the steady state. But we are looking at finite horizon, so a lot of those complexities goes away. Okay. Any?
Temperature control example.
Yeah.
Is there any way to visualize xt?
Xt is the temperature of the room.
Okay.
That's the slow dynamics. Do you think that the temperature changes every millisecond?
No, but
No.
if we want to change the equilibrium state, then it does.
Yeah, but it still changes very slowly. This epsilon, there is this epsilon term. So xt plus 1 is almost close to xt. Okay, with some small change, very small change. Any other question? Okay. Okay, perfect. So we have all these assumptions. I don't think we need any additional assumption. Oh, there are also other assumptions on the fact that this should satisfy the second order sufficient condition for optimality and all that stuff. So I'm kind of suppressing a lot of other assumptions that are made here. Technical assumptions for the algorithm to work. But I'm not going to cover those assumptions, but know that there are more assumptions here. Like the second order sufficient condition must be satisfied for this entire problem at all values of xt and yt. Okay. So now the question is, how do I approximately? So of course, if I want to solve this problem, I have to apply dynamic programming. And to solve it, I don't even need these assumptions. So what I've done is I've made these assumptions in order to make my life easier and to run a simpler dynamic program in order to solve this problem and get an approximately optimal pi t. We don't want truly optimal pi t, we just want approximately optimal pi t. The story of this algorithm is as follows. A student asked me to sit in his candidacy exam back in 2019, and he was doing some black magic with singularly perturbed system. And I said, why are you doing black magic? There has to be a white magic to do it. And so I formulated the problem, and like a good advisor, I passed it on to my student, and then my student solved the problem, and we wrote a paper about it. So if you are doing black magic, do call me for your candidacy exam. That's the upshot of this discussion. Okay, so what do we do? Okay, so what do other people do? What was the current state of the art before we solve this problem? So what other people do is, let me tell you what they do. So I'm going to define a bunch of functions. So f1 eta of xu equals to f1 x c t eta of xu and then I'm going to minimize C capital T xt plus 1. So replacing yt plus 1 with eta. Okay. Ct x Ct eta xt ut t equals 0 to capital T eta, whatever the yt is, whatever the equilibrium yt plus 1 is going to be at that point. And then I'm going to have gamma t that maps xt to ut, and then I am going to So let's look at this optimization problem. We actually don't have a terminal cost in our paper. I'll keep the terminal cost here, but in the paper we don't have the terminal cost. So what do you think the problem has become in this particular situation? Let's ignore the terminal cost for a bit.
In our rocket launch problem, the terminal cost was
Reaching Mars or reaching Moon or wherever you want to reach. Okay. We'll talk about the rocket launch when we talk about look-ahead approximation. Okay. One thing at a time. Right now we are optimizing air conditioning system of this room or your car. So what is the way to solve this problem, or a simple way to solve this problem? So I have this problem over xt and yt. So this policy is very complicated because it takes as input both x and y. What I have done is I have converted that optimization problem into a simpler problem where my policy only takes as input xt and solves the simpler optimization problem. Okay, not the complicated optimization problem. So once I solve this optimization problem, I get my gamma star t by solving this particular optimization problem. I can solve this using dynamic programming. Now, what do you do about this fast dynamics? So what have we done? We have looked at the slow dynamics. We have looked at what the temperature of the room is. We converted the optimization problem in a way that we assume that yt will always be at the steady state. Yt will always be at eta xt ut at all points of time. So we have replaced, wherever you see yt here, we have replaced it with eta of xt ut in all of these functions. Okay, so we have assumed that yt will reach equilibrium immediately. As soon as I change x and u, yt will achieve equilibrium immediately, and that allowed us to simplify because now yt is no longer a variable, it's just a constant which depends on x and u. So I change my cost functions, I change my constraint, and then I solve this problem and I get gamma star of xt, which gives me ut. Is that good enough? Is that good enough approximation? So it turns out that actually this is a good enough approximation. You do have, so you came up with this, whatever the cost function is, you get this action and you implement this action and you will be suboptimal. You will be suboptimal because you haven't corrected for the fact that yt itself has a dynamics. So we need to come up with a correction factor for yt to be a dynamics because yt is a dynamic. So so what would people do? Let me write it down. So I want my policy pi hat t of xt and yt to be a function of gamma t star xt plus another function mu t star of xt and yt minus eta xt ut. So this is my deviation. and this is my correction. To optimal action. Correction to action due to fast dynamics. So here is how you could potentially solve this problem. You generally want this particular state to be as small as possible, and you want to correct. So this is your optimal action that was computed using this particular approach. You want to correct that action slightly so that this deviation is as small as possible over a long period of time, and your effort, your action effort, which is this part, has to be as small as possible. So what do? Well, you run a LQR algorithm for minimizing the deviation, a quadratic function of the deviation plus a quadratic function of this correction term, and that was the black magic there. So at the high level, you solve this problem for the slow dynamics, and then you make a correction by running a tracking algorithm in the fast dynamics. Okay. What is the problem with that approach? If you run an LQR with the fast dynamics in order to come up with this correction factor? So yeah.
Can you confirm that like YT will be within the constraints if you run an LQR on it?
That's why it won't be in the constraint. So then they do additional band-aid solutions in order to make sure that those constraints are always met. Okay, so that was the problem with this approach. Yeah.
Isn't this pi or star of t plus 1?
No, this is my pi t.
So in that case, shouldn't this be gamma star xt minus 1?
No, pi t is a function of xt, yt, and it maps to ut. So I'm just using the action computed here plus a correction term. And this is my approximately optimal solution. Okay. So if you bought a car pre-2015, what is typically happening is there is no cost function to be minimized. They don't care about the cost function. They have a handcrafted gamma star t, and then they run a tracking algorithm or a PID controller in order to make sure that this particular deviation is as small as possible at all points of time. So that's the way to do it for, that was the pre-2015. Then post-2015, people said, oh, we want smart cars, we want sophisticated cars, we want fancy cars. So then they said, okay, let's do the optimization at the high level and put PID controller or a linear quadratic regulator at the low level, at the fast dynamics level. So that's the current state of the art. So you solve some optimization problem at the high level, at the slow dynamics level, and then you let a tracking controller take care of the fast dynamics. And now what we are doing is we are looking at the optimization of the fast dynamics, and then we are correcting using another optimization algorithm for the slow dynamics. So sorry, we do solve this problem for the slow dynamics, and then we do another tracking problem for the fast dynamics. So let me set up the tracking problem now. I have about 10 more minutes. Any questions so far? I'm going to erase all of this side of the board.
What if you build some information for what happens without that new t term?
This constraint gt less than equal to 0 may not be satisfied. If you just run a tracking algorithm here, you will not be able to satisfy the constraint. It's not provably satisfied.
What does that mean in practice, though? What would happen?
Right. So in practice, it might mean that your car has much higher carbon emissions, CO2 emissions, or NOx emissions, because you are accelerating the engine in a very, very different manner. So if you're, for instance, if you are trying to optimize your battery lifetime, or if you're trying to optimize your emissions, or if you're trying to optimize your fuel, it means that you might have, like, many of these problems have constraints. Like, for instance, distance with the vehicle in front, that's a constraint. Now, you may not meet the constraint. Does that mean you are driving dangerously? Kind of. But does that mean you will be in a crash? Probably not. Does that make sense?
A little bit, yeah.
Sorry?
I said a little bit.
Yeah. So let's say this is the temperature constraint, that the temperature of the room should not go above 75 degrees Fahrenheit. But once in a while, you will go above 75 degrees Fahrenheit. Is that a problem? Well, in data centers, it is a problem. If you are not in data centers, it's not a problem. So we don't think about it. But in data centers, they have like service level agreements with the chip manufacturers, that the temperature of this data center will always be between 70 to 75 degrees Fahrenheit. It cannot go above 75 degrees Fahrenheit. It cannot go below 70 degrees Fahrenheit. So they have those agreements. And in that case, you really need this constraint to be satisfied at all points of time, because it's a legal contract between two very large entities. Same thing in autonomous vehicles. It might be okay for you to be close to the vehicle in front, and there are many drivers like that who just tailgate you on the highway, and I don't like it. Does that create a problem for me? I mean, it creates an uncomfortable situation for me, but it's not like I've been in a crash, right? However, an autonomous vehicle cannot tailgate. Like, by law, they cannot tailgate. So that constraint always has to be satisfied. So those are the situations where we care about this constraint a lot. Any other question? Okay, so I'm going to define my Q of t of xt yt ut as let me call this v eta t plus 1 xt plus 1. Sorry? We are trying to come up with the computation of this mu t star, right? So until now, people use tracking controller to come up with this mu t star. We are trying to come up with a different type of tracking controller.
So we're going from PID to something new?
Something new, yeah. And then I'm going to define qt eta xu as qt this thing comes from the slow dynamics optimization. From here, okay? And then we come up with another optimization problem where I want to minimize. Let me define another thing, zt equals to yt minus eta xt ut, and Vt equals to Ut minus gamma T star Xt. Oh, I'm using Vt twice. This is a small v. Small v, let me use this to denote small v. And then I want to minimize over v, v in, I think let me just keep it v, minimize gradient of y qt xt eta xtut ut transpose z such that g eta t xtut I'm going to minimize it with respect to Vt. And remember that Vt is actually ut minus gamma star t xt. So it's a function of both xt and ut. So this is the way to set up the optimization problem correctly. And what happens is if you solve this particular problem in order to come up with Vt star, so you can name Vt star, which comes out of this, as mu t star xt and zt. Whatever is the optimal solution here, if you name it mu t star of xt zt and you plug it in here, you get an approximately optimal solution to the original problem that we wanted to solve, the original problem that was written here. Now the thing is, if you use PID controller, you will not meet the constraint. On the other hand, if you use this type of optimization algorithm for computing mu t star, you will actually never miss the you will not lose this constraint. And if you can make this constraint more complicated, so this is the first order constraint term, but you can make this constraint more complicated in order to make sure that you never miss the constraint at any point of time during your operations. So there are multiple ways to handle those kind of situations which we talk about in the paper. But basically this gives you a very good estimate of mu t star, and with this particular algorithm I can prove that this is an approximately optimal solution. This pi hat t constructed in this way is an approximately optimal solution to the original problem that we wanted to solve, and it meets the constraint most of the time. Actually, by putting a bit more constraint on Vt, you can show that this particular thing meets the constraint at all points of time. So roughly that was our contribution in this case. What we are doing is not solving the optimization exactly, which is a very complicated optimization problem, but instead distributing the optimization into two separate forms of optimization. One is a slow dynamics optimization, which I can run separately, and then do a fast dynamic optimization, which can be accomplished in a much faster time scale, and then use that optimal solution of the fast dynamics along with the slow dynamics to come up with the approximately optimal solution. So any questions on this before we, yes? Yeah, it's from this particular slow dynamics, yeah. Any other question? Yes.
The baby there is missing T.
Sorry?
The mean weight, the mean.
Yes, here.
Okay, I think there should be a T.
Oh, yeah, of course. That's right. Correct. That's right. Okay. So this is one of the ways by which we do approximate optimization of the original problem. There are a bunch of other papers as well which we have written on this topic for different kinds of optimization approximations. So this is just one of the many papers we have written on this. In the next class, we'll talk about look-ahead approximation, which means I have a 1 million time step problem or a 2 million time step problem. How do I solve a 100 time step problem or a 10 time step problem and still maintain some sort of approximate optimality of the overall 1 million step optimization problem? So think about it, and we'll discuss it on Monday. Thank you. Have a great weekend.